All right, so this problem really exemplifies how we use forces and motion together. We're going to analyze everything sort of separately in this next problem, but it really is sort of our introduction to how forces and motion come into play and how we can utilize both analysis methods that we've learned to solve problems. So this problem reads, a 2.5 kilogram firework shell is shot straight up by a mortar. It reaches a height of 110 meters. The first part is, we're going to neglect air resistance in this problem. The first part is, what is the velocity of the firework as it leaves the mortar? The second part is, if the mortar is 0.45 meters long, what's the average acceleration of the firework in the mortar as it travels? And then how does that relate to the average force? So if we break this problem down and think about what's happening with this firework, it's in a mortar. A force is being exerted on that firework through the mortar, and then it leaves the mortar and is now in free fall. So can we use the motion to figure out how much force the mortar exerted on the shell? Okay, so the first part of the problem asks us, how fast is it going at the point it releases from the mortar? So that's a velocity. That's a kinematics process. And so we'll follow our kinematics approach where we look at the object first. Well, that's the firework. We'll call it the shell. Okay, and we define what begins the motion that we care about and what ends the motion. Well, it's beginning when it leaves the mortar. That says motor. It leaves the mortar casing. All right, that's better. And it ends when it reaches the peak. That's the motion that we're interested in. So in kinematics, we have to draw our picture and identify. So here's the mortar. We'll say that the firework travels out. And I'm going to say that this vertical position is position 0. Great. So let's look at our list of variables. We have initial position, final position, initial velocity, final velocity, acceleration, and time, all related to the motion I've defined. So my initial position, well, I've defined that location as 0. I'm told when it reaches the peak, it goes to 110 meters, so I know my final position. I don't know my initial velocity. That's the velocity that it leaves the mortar. I don't know. I know it's moving, but I don't know how fast. The velocity at the peak, well, it reaches 0 velocity at the peak as it changes direction and comes back down. As it's traveling through the air, it's in a state of free fall, so we know the acceleration is 9.8 meters per second. We're not given any information about how long that process takes. So part A asks us how fast is it going when it leaves the mortar. And so we're really interested in the initial velocity as it relates to the motion I've described. I don't know time and I don't know initial velocity, but I know everything else. So the equation that's going to help us the most in this case is the one that tells us that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And so my final velocity squared is 0. Initial velocity, I don't know. That's what I'm interested in. Plus 2 times negative 9.8 times my final position minus my initial, which is 110. All right. So when I solve for the initial velocity, in this case, I have 2 times 9.8 times 110, and I'm going to take the square root of that value, and I either have a positive velocity or a negative velocity. Whenever we take a square root, we have both positive and negative, but the rocket's moving up at this case, and it has a velocity of 46.4 meters per second. So this is part A. All right, how fast it's moving as it leaves the mortar. Part B asks us if the mortar itself is 0.045 meters long, What's the average acceleration as it goes from the start to leaving? So as the shell leaves the mortar, from sitting at the bottom to leaving the mortar. Well, that's a new problem. That's a new problem. We have the same object. The object is the shell. Is our object. Our initial now is when it's at rest at the bottom. So at rest in the mortar. And our final is when it leaves. All right, so we'll draw a picture. Here's that mortar. Here's that shell at rest inside. In this case, I'm going to say that at the bottom here is my position 0. I'm in a new problem, so I can define a new origin. So we want to look at our initial position, final position, initial velocity, final velocity, acceleration, and time. We're saying it starts at the bottom. We know the mortar is 0.45 meters long, and so this position is 0.45 meters. Just want to double check that length. Yep. The initial velocity, well, it's going to start at rest at the bottom. How fast is it going when it leaves the mortar? Well, we figured that out in part 1. So that's 46.4 meters per second. I don't know the acceleration. This is not the acceleration due to gravity. This is the acceleration as it's traveling through the mortar. And I don't know the time. We're interested in solving for this acceleration. And once again, I don't know time, so I'm going to utilize that same equation, final, that I did before when I didn't know time and I knew everything else in it. So V final is this 46.4 quantity squared. V initial is 0 plus 2 times the acceleration I don't know, and my position displacement is 0.45. And so if I solve for the acceleration, we have 46.43 squared. And then I divide it by 2 and divide it by 0.45. And I get an acceleration is equal to 2,395 meters per second squared. Whew. That that shell is moving. This is the average acceleration, so our part B. The third part says, well, what's the average force? What's the average force on the shell in the mortar? Well, we know that the average force, the net force, this is part 3, is equal to the mass times the acceleration. Well, my force is equal then to the mass, which we were given in the problem, is 2.5. I didn't write it on the board, but that was the mass, times my acceleration of 2,395 meters per second squared. So we get an average force of 5,988 newtons acting on that firecracker. Now, it does also ask us, what is this answer in terms of the object's weight? How many G's does this firecracker fill? Well, if we're going to look at the ratio of the force to the weight, we need to know the weight. Remember, the weight is the force of gravity, which is equal to mass times gravity. So our weight, which is 2.5 kilograms times 9.8, gives us 24.5 newtons. So if I take a ratio of 5,988 to 24, 5,988 to 24.5, I get a ratio, so 5,988 divided by 24.5 of 244 G's of force that mortar is feeling. So, a lot of G's coming off in that firework. All right, so recognizing, what does this tell us? We did these in 3 steps. We did kinematics, we did forces. But it leads us to get an appreciation that if I can determine the force acting on the object based on the motion, or the reverse, I might be able to determine the object's motion based on the force of the object. All right, good job.